Good morning. All right, so we are actually going to do some math today. So the section that we're actually going to be in, and before we do that, real quick, are there any questions that have come up in the past 24 hours since we met yesterday? Any issues anybody's running into, questions you got about how things are going to work? Let's start with that before we jump right in. And again, if you want to ask a question, feel free to use the raise my hand button at the bottom. And then you can also type in the chat, or if you want to turn on your microphone and ask a question, you can do that. Okay, so this is section 1.6. So this is the section from chapter 1 that we skipped over. So we're going back to that before we move on with chapter 3, because we need the information from this to do the next section in chapter 3. Any other questions before we get started? All right, if anything comes up, just let me know, and I'll be happy to answer any questions you might have. All right, so section 1.6, we're going to look at complex numbers today. And again, remember, this whole session is recorded, so if you ever need to go back and look at anything, feel free. The slides are available. So I'm probably not going to spend as much time on the slides that have just the information on them. I'm going to spend more time on the slides where we actually work through stuff. So in this case, a complex number is any number that we can write in the form a plus bi. So anytime we can write it in this form right here, that's what we're going to call a complex number. This a part right here is actually a real number. So a is going to represent a real part. And then the bi is going to be the imaginary part of that, where the I represents the imaginary number. Now, you might be asking yourself, well, what does I even mean, right? What does it mean to be an imaginary number? The way we're going to get I is that I squared is equal to -1. Well, if we think about that, if I squared equals -1, the way we would actually find I, and real quick, can everybody see that okay, what I've written, or does it need to be darker? So if you will, in the chat, just tell me if it's okay. Looks like most people are okay with that. Okay, so again, if it needs to be darker at any point, let me know. Or if anything's getting blurry, let me know, and I'll try to resolve those issues. All right, so if we've got I squared is equal to -1, if I just want to know what I is equal to, what I'm going to do is I'm going to take the square root of both sides here, and that means that I is equal to the square root of -1. So that's the value of I that we're always going to be looking at. So remember, before we said, if you ever get the square root of a negative number, it's not going to be real and we didn't have a solution. Well, now we have a way that we can say, well, if you do get a negative under a radical, if you have the square root of a negative number, now we can just call that an I value. And so now we can call all of these solutions imaginary solutions instead. And what this is going to be useful for is when we jump back to chapter 3, when we're trying to find all the solutions, all the zeros to those polynomials that we were looking at before the break, if we have any that have those negatives inside the square root, then we can just say, oh yeah, those are imaginary solutions now, but we can give them a specific value. Okay, and those values are going to look like this form, a plus bi, when we find them. Okay. And then the last part of this just says that two complex numbers are going to be equal if and only if the real parts are the same and the imaginary parts are the same, right? So it can't just be one or the other. Two imaginary numbers for complex numbers are equal if both of those pieces are exactly the same in those complex numbers. Okay? All right, so let's jump into some examples now and see what we can do with these. So the first thing we're going to do here is just identify the real part and the imaginary part of each of these. So if we're looking at this now, the real part is going to be the part that does not have an I. So if I'm identifying the real part, for this one right here, the real part is just going to be 3. If I'm identifying the imaginary part of this, we're only looking at the value of the I. So I don't have to include the I, so the imaginary part of this is just going to be 4. And the reason I say that is in your WebAssign assignments, it's going to ask for what's the real part, what's the imaginary part. And so just be careful when you're entering the imaginary part that you're only putting the number, you're not putting the I with it, because if you put the I in there, it's not going to give you credit. Okay, so the real part here is the 3, the imaginary part just 4. Any questions on that? All right. I'm going to try to do a little bit of feedback stuff here, even without microphone. So feel free to type in the chat if you think you know the answer when I ask a question here. So if we look at the second one, what does it look like the real part is going to be? Good, right? So 1/2 is the real part. And then our imaginary part would be what? Right? So -2/3 in this case, right? Because we want to make sure we're keeping the sign with the value. So our imaginary part this time is actually going to be a -2/3. So that's the key here, is just make sure if there is a negative or a subtraction, just keep that sign with the value. Any questions on that one? All right, so now if we look at this next one down here, we've got 6i. Well, if it's just 6i, what do you think the real part is going to be? Good, right? So since there is no real part, we're just going to say the real part is 0, which means in this case, the imaginary part is going to be what? Awesome. Just 6. Okay. So again, anytime there is no real part, then we just put 0 as that part, and then we only use the number for the imaginary part. And then our last one down here, -7, what's going to be the real part for -7? Good. So -7 is the real part. What's the imaginary part then? So since there is no imaginary part, we're just going to say the imaginary part is 0 this time. Any questions on any of those now? Just identifying real and imaginary parts of complex numbers. All right. So now, we also have what's called a pure imaginary number, okay? And a number such as 6i that we looked at in the last example would be what we call pure imaginary, because there is no real part, right? The real part is 0 there. So just keep that in mind. If it doesn't have a real part, we call it pure imaginary. Now, some of our properties here of addition, subtraction, and multiplication for these numbers, it's basically like adding and subtracting and multiplying like terms, okay? So adding and subtracting like terms for the first part here. We can add the real parts. So the A and C are both real parts, so we can add those together. And then we can just add together the coefficients of the imaginary parts, so we can add the B and the D together and just keep the I. So really, it's just like combining like terms with variables. Okay, that's kind of what we're doing when we add and subtract these imaginary complex numbers. Now, if you have a complex number times a complex number, you can almost think about that as like multiplying binomials. So we're going to have to use FOIL to multiply these. So we're going to multiply the A times the C. That's going to give us this piece, the AC. We're going to multiply the B times the BI times the DI. That's what gives us this piece down here, and I'll explain in just a minute why it's a minus. Then we're going to multiply the A times the DI. That's going to give us the A times DI. And then the BI times the C is going to give us this last piece, the BC times the I. Again, I wouldn't stress too much about knowing this formula, because you're pretty much just going to take what we've got here, you're going to use FOIL, and then you're going to combine like terms and simplify. Okay, so just anytime you're adding or subtracting, combine like terms. Anytime you're multiplying, use FOIL, and then we'll simplify from there. Okay. Any questions on that slide? All right. Let's take a look at an example then. Okay, so the first one here, we're just adding together these two complex numbers. So if we combine the real parts here, what should that give us? I'll give everybody a chance to kind of catch up and get that written down if they want to. All right, so now looking at that first one here, if we add together the real parts, good, right? So Kenneth says we'd add 3 plus 4, that should give us 7. So it's just like we're combining like terms. And now if we combine the imaginary parts, what should that give us? So if we have a positive 5i and then a negative 2i, good. So it's going to give us a 3 as the coefficient. And in this case, we're actually going to even include the I because we're trying to get it into that form a plus bi. So this is going to be positive 3i now. Okay, so that's kind of the difference now between just identifying the real and imaginary parts and actually expressing these in the form a plus bi. We actually do want to include that I when we write our answer now. So we have 7 as our real part, and then 3i is the complex imaginary part of that number now. Any questions on that one? All right, so now let's look at the subtraction one. So now if we take 3 plus 5i and we subtract 4 minus 2i, what are we going to get for that real part this time? Good. So we have negative 1. And now if we combine the imaginary parts, we have 5i minus a negative 2i. So what should that be? Good. So we get a positive 7i, right? So again, don't forget the I part of this. Okay, so it's going to be plus 7i for this one. Any questions there? All right. So now we have the multiplication down here. So again, we're going to use FOIL to do this. So if we start with our first terms, what are we going to get for the 3 times 4 part? Good. So 12. Now we can go to our outer terms. So that's going to be the 3 times the negative 2i, which will give us what? Good. Negative 6i. Inner terms here, 5i times 4 would be what? Good. Positive 20i. And then finally, we're going to do our last terms, 5i times negative 2i, which would be what? Almost. There we go. Negative 10i squared, right? So negative 10i squared, because we're multiplying, in this case, an I times an I. That's why we end up with an I squared down there this time. All right. Now, let's think back to what we learned on one of those slides. Whenever you see an I squared, what is I squared equal to? Oops, sorry, I got blurry. Good. I squared is just negative 1 now. So everywhere I see an I squared, I'm just going to replace that with negative 1. So we have 12 minus 6i plus 20i minus 10 times negative 1. So anytime you end up with an I squared, make sure you change that to a negative 1 because we know that I squared equals negative 1 now. Now we can go through and combine like terms. So if we look at this, our real parts are now the 12 and then this negative 10 times negative 1. Well, if we combine that, what should we end up with? Good. It's going to be 22 total, right? Because this becomes positive 10 and we're adding that to the 12. So our real part now becomes 22. Now, if we combine the imaginaries, we have a negative 6i plus 20i, which should give us what? Perfect. Plus 14i. And that would be our final answer now because, again, in the direction says get it in the form a plus bi. Now we have our a real part and our b imaginary part. Any questions on any of the steps for that one now? All right. Now, this last one's the fun one. All right. So we've got I to the 23rd power. So here's what I want to do. I'm going to start by just saying, let's go through and do like I to the second power, I to the third power, I to the fourth power, right? And just keep going just to see if maybe we can recognize any kind of pattern there. And then we're going to try to take that pattern and figure out what I to the 23rd would be equal to. All right, so I'm going to start over here, and I'm just going to say, well, if we just have I, that's just an I, right? So I to the first power here is just an I. Now, if I want to do I to the second power, what is I squared going to be equal to? -1, right? Okay, so that one we know. Okay, now, if I want to know what I to the third power is equal to, what do you think that might be? Okay, not quite. So we're not quite 1, because if you think about it, the way we could get I to the third, remember with multiplication, add exponents, so we could actually multiply this I squared times this I to the first. So I to the third should actually be the same as I squared times I. That's right. And so if we multiply the I squared value times the I value, that's just going to give us negative I, right, or -1I. Any questions on why that is? Okay, so get I to the fourth power then. So what do you think I to the fourth power would be equal to? Good, right? And so in this case, it's going to be equal to 1, because the way we could break this down is we could say the same as I squared times I squared. But we know I squared is -1. Another I squared would be -1. And a -1 times a -1 would actually give us a +1 now. Now, if I want to go to I to the fifth power, what do you think I to the fifth power is going to be equal to? Good, right? 1I. And the reason it's going to be 1I is because we're taking this I to the fourth that we just got, and we're just multiplying by another I to the first power, right? Because I to the fourth times I to the first, that would give us I to the fifth. Well, we know I to the fourth is just 1, and then I to the first is just going to give us I. So 1 times I is just I. And now what's going to happen is we're going to end up repeating all of these values if we just keep raising that exponent by 1 each time. So I to the sixth is going to be the same as this one, so we'll get -1. I to the seventh is going to be the same as this one, so -I. I to the eighth would then give us 1 again. I to the ninth would be this one. And we're just going to keep going through those 4 values over and over and over again. So now, if I want to know what I to the 23rd power is, the easy way to do that, since this thing's going to repeat before, that's right. So there's a pattern in this case, right? So every 4 exponents, it's just going to repeat those values over and over again. And so what we want here, since we know it's going to repeat every 4, I'm going to take the 23, I'm going to divide it by 4, and I'm going to try to figure out what my remainder would be. So how many times does 4 go into 23? 5 times. And then if we multiply that, what's our remainder going to be? Good. So we have a remainder of 3. In this case, the pattern is this. If we have a remainder of 1, then we're going to have I. If we have a remainder of 2, it should be -1. A remainder of 3 should give us -I. And then a remainder of 0. And the reason it's 0 and not 4 is because if it was 4, then 4 would still go back into 4, right? So a remainder of 0 in this case is just going to give us +1. So that's the pattern we need to know. So our remainder this time was 3. Therefore, our answer should be -I. So that's kind of the short way. So if you have like I to the 176th, rather than trying to figure out, okay, if I keep multiplying by over and over and over again, where am I going to end up? Just take that value, divide by 4, find your remainder, and then just follow this pattern over here to figure out which value it's going to be. So those are the rules for any I to some power. So anytime it's just I to an exponent, this is the work we can do, and we can always follow this pattern over here to figure out what our value would be. Does that answer your question, Naomi? Any other questions there? All right. Anybody need more time to get that before I move on? Because I want to make sure everybody's got these rules over here. Okay. And again, if I ever do move on too fast, stop me, right? Or if you need to, you can always go back and look at the video too, because it'll be there. All right. Next slide, complex conjugates. Okay, so whenever we have a complex number, a plus bi, right, and we're going to call that number z, we can define a complex conjugate, z bar is the way we read that, so it's just a z with a line over top, is going to be a minus bi. So notice here, we kept the real part the same, and we just changed the sign on the imaginary part. So whenever you're talking about a complex conjugate, all we're doing, keep the real part the same, change the sign on the imaginary part. And the reason for wanting to know these is because if we take a complex number and we multiply by its conjugate, you're going to end up with something that looks like this, where there is no imaginary part anymore. The times we would want to do that is, let's say we have something like we have down here, where there's an imaginary part in a denominator of a fraction. Because that's like a square root in a denominator now, we don't want to leave it there. And so we can always multiply by the complex conjugate, and that's actually going to get rid of that imaginary part denominator. Okay, so this is when you would want to do this. If you're dividing complex numbers, you have an imaginary part in the denominator, you're trying to get rid of it, we can just multiply top and bottom by that complex conjugate. Okay. And again, I'm not going to take a ton of time on these slides because, again, they are posted, and you can always go back and access them. So I'd rather just focus on the examples at this point, okay, and see how these are going to work. So let's take a look at this example here. I'll give you a chance to write it down. All right. So if we're trying to divide 3 plus 5i by 1 minus 2i, again, this is one of those cases where we have that imaginary number in the denominator and we want to get rid of it. So what do you think I would want to multiply by here to get rid of that imaginary number in the denominator? Good. So its conjugate would be 1 plus 2i. So that means on the top and the bottom, I'm going to multiply by 1 plus 2i. Now, this is one of those cases where we're going to have to use FOIL because we're multiplying a complex number times another complex number. So if you want to, we can group these together, And so now if we use FOIL, we're going to start here with 3 times the 1. So that's going to give us 3. Then we can do our outer terms. 3 times 2i is going to be a positive 6i. Inner terms, 5i times 1 is going to give us a positive 5i. And then 5i times 2i is going to be positive 10i squared. So that's just our numerator now. Now we're going to do the same thing in the denominator. So we got to use FOIL again. We do that. We have 1 times 1 is going to be 1. Outer terms, 1 times 2i, positive 2i. Inner terms here, negative 2i times 1 is going to be a negative 2i. And then our last term is negative 2i times 2i. It's going to be a negative 4i squared. Okay. Now, at that point, remember we said that I squared is equal to what? All right, so all those I squares, I'm going to switch over to negative 1s now. So we end up with 3 plus 6i plus 5i plus 10 times negative 1 over 1 plus 2i minus 2i minus 4 times negative 1. Right? And if you want to start combining steps, right, combining like terms at the same time that you're switching those over to negative 1s, or if you just recognize them as negative 1 and want to just change signs, right, I'm fine with that. You don't have to write in every single one of these steps every time. All right, so now let's see if we can combine some like terms, though. So if we look at the real parts in the numerator, what are we going to get when we combine those real parts? Good, negative 7, right? So we have a 3 plus a negative 10. That's going to give us negative 7. What are we going to get when we combine the imaginary parts in the numerator? Good, so positive 11i. So that takes care of the numerator. Now, if we look at the denominator, what's going to happen to our imaginary parts? Cancel out, right? So these right here are opposites. Those are just going to cancel. And so now we really only have to worry about combining those real parts, and that should give us what? Positive 5, right? Because this becomes a positive 4. 1 plus 4 gives us 5 in the denominator. Now, the little thing we want to make sure of here is that we express it in the form that they want. So they want it in a plus bi form. So we actually want a real part and then an imaginary part here. So all I'm going to do is I'm just going to separate out this real part and this imaginary part and write this as negative 7 over 5. There's my real part. Plus 11 over 5 times I. And the reason for that is, again, in WebAssign, they're going to really be strict that you put it into that form right there. So we can't just leave it as that fraction. We actually have to have a real part and an imaginary part there. Any questions on that one? All right. So I'll give you a chance to go ahead and write down the next one. All right. So now if we look at this next one, what's going to be our conjugate that we're going to multiply by this time? Good. Negative 4i, right? Because remember, we said the conjugate should have the opposite sign for the imaginary part, and we're going to keep the real part the same. Since there is no real part, that's just going to stay 0. And if we take the opposite here of 4i, that's just going to be negative 4i. So we're going to multiply top and bottom by negative 4i. Now, if we do that, right, this time it's not going to be FOIL because we only have one term that we're multiplying. So we can just distribute this to each of our terms over here. So what's 7 times negative 4i going to give us? Good. Negative 28i. And then if we multiply the negative 4i times the 3i, what should we get there? Negative 12i squared. Perfect. Okay, and now if we look at our denominator, we have positive 4i times negative 4i, and that should be what? So, Sarah, are you asking if that's correct or why it's correct? Sorry. Yes, right? So up in the numerator, that negative 12i squared is what we should get when we multiply that. Good. All right, so now if we're looking at the denominator, we have the 4i times the negative 4i, and good, that's going to give us a negative 16i squared. Any questions up to that point? All right. So now, remember, we can change our I squares to negative 1s. That's going to give us negative 28i minus 12 times negative 1 all over negative 16 times negative 1. So now if we simplify that, what should the numerator look like? Good. If 28i, and that's going to become plus 12. And then our denominator is just going to be what? 16. Good. And Sarah, the way you wrote also correct, right? So if you had done 12 minus 28i, you can switch those terms. And that's actually what I'm going to do in this last step, since we wanted in that a plus bi where the real part is first, the imaginary part second. So if I do that, and I put my real part first, that's going to give us 12 over 16 minus 28 over 16 times I. Now, always simplify. So if we look at each of these fractions, what would we get if we were to simplify 12 over 16? Not quite, so not 1/4. Good, right? So 4 goes into both of these. 4 goes into 12 times. 4 goes into 16 4 times. That's going to give us 3 over 4. And then we want to do the same thing with the 28 over 16. So what would that be if we simplify it? Good. 7 over 4 I. Okay. And so this right here would be our final answer for that one now, because we have our real part and we have our imaginary part. Any questions on those now? All right, does anybody need more time to get any of that work now before I flip to the next slide? All right. All right, so square roots of negative numbers, right? And so this is why I said this is going to be important, is when we're finding these roots or these zeros of our functions, if we end up with the square root of a value, then we can just say that the square root of any negative real value is going to be I times the square root of the positive R value. So basically, if you have a negative in there, just bring it out as an I, and then we can simplify from there. Now, when we're taking these in actual equations or polynomials, right, if we're looking for zeros, what's going to end up happening is we're going to end up with a plus or minus when we take that root. And so we're actually going to get a positive I times the square root of whatever and a negative I times the square root of whatever. Okay, so these are going to actually exist together because of that plus or minus that we get when we actually take a square root. And again, I'm not going to take a ton of time on that slide, okay, because I'm going to show you in the example how this is going to work. All right, so let's take a look at this first one here. So if we've got the square root of just -1, what should the square root of -1 be equal to, just based off what we could do from that last slide? right? So we can bring the I to the outside, and then we can keep the square root of 1 here. Now, always simplify your square roots where possible. So if we look here, what is the square root of 1 going to be equal to? 1, right? So this becomes I times 1, or I times 1 would just be equal to I. Okay. One that you might be able to do without doing all the steps to simplify, right? Because the square root of -1 should just be equal to I, but in this case, it's because we can bring the I out, we can take the square root of 1, and I times 1 gives us an I there. And so let's look at the next one. So what could we do first with the square root of -16? Almost, okay? So you're on the right track. So the first thing I'm going to do, I'm going to bring out the I. I'm going to keep the square root of 16. What's the square root of 16, though? 4. Good. So this becomes I times 4, which would just be what? Good. 4I. Okay. Any questions there? Okay. All right, and so same thing on the last one, right? We have the square root of a -3. So my first step is just to go ahead and bring the I outside. So we end up with I times the square root of 3. And in this case, the square root of 3 is irrational. We can't simplify it. There are no perfect squares that go into 3. So that's actually going to be our final answer for this one because it does not simplify anymore. Okay, so there will be cases where you get something that's not a perfect square here. There are no perfect squares to simplify it, and so you can just answer just like that. Any questions on any of those now? All right. Now let's take a look at this one. Okay, so I'll give you a chance to write it down, okay, but we are going to be in FOIL, but then we're going to make sure we put our final answer in A plus BI form. All right, so if we take a look at this one, the first thing we always want to do first is simplify our radicals, okay, and especially any radicals that have negatives inside. Okay, so you can't start multiplying using FOIL until we simplify the radicals first. I'm going to go ahead and look at this square root of 12 right here. I'm going to ask myself, do we have any factors that go into 12 that are perfect squares so that I could simplify this? So is there a way I could break that down? 4. Okay, so we can simplify this into the square root of 4 times 3, since 4 is a perfect square that goes into 12. So that's my first step. Now I'm going to come over here to the next term. And if we look at the square root of -3, what can we bring out of that square root? The I. Good. So this is going to become I times the square root of 3. Now I'm going to go into my next set of parentheses. The 3 is just a 3, right? So I'm going to keep that. But then we can bring what out of the square root of -4? I. And good. So this one, if you want to go ahead and bring out the entire 2i, we can do that, right? Because the square root of 4 would be 2, and the square root of a negative would give us I. Right? So that is going to simplify to 2i this time. All right, now let's come back to this square root of 4 times 3 that I wrote right here. What is the square root of 4? 2, right? So now I can bring the 2 outside, so that's going to give us 2 and then the square root of 3, the 3 stays inside. Everything else down, I square root of 3, and then 3 plus 2i. Now that we've simplified all of our radicals and we don't have any negatives inside of our radicals, that's the key part, now we can actually FOIL this out. Okay, so we're going to start here. We've got 2 times the square root of 3, and we're multiplying that by 3. When we do this, you're basically going to multiply anything on the outside of your radicals and then keep those on the outside. Multiply anything on the inside of the radicals and keep that on the inside. Well, since I only have a number on the outside here, I'm just multiplying that by 2. So that's going to give us 6 times the square root of 3 for that first part. Now we got to do our outer terms. If we multiply our outer terms here, what do you think that's going to give us? Okay, so we are going to get a 4i, and we have a square root of 3, right? So we're going to get plus 4i times the square root of 3. So we multiply the 2 and the 2i to get the 4i, and then we have to keep that square root of 3 there. Okay. Now we're going to do our inner terms. So what are we going to get when we multiply our inner terms? Good. Minus 3i times the square root. And then finally, we have to do our last terms. So we have this negative I square root of 3 times a 2i. What do you think we're going to get with that? Perfect. Negative 2i squared times the square root of 3. So we have a negative I times 2i is negative 2i squared, and then we have that square root of 3 that we have to keep there. Any questions up to that point? Okay, so now we know I squared should be equal to what? Good, negative 1. So I'm just going to go in on my next step and change that I squared to a negative 1. That's negative 2 times negative 1 times the square root of 3 now. And now we can start combining like terms. So if I look, I have a 6 times the square root of 3, and this is going to become a positive 2 times the square root of 3. What am I going to get when I combine those then? Good. 8 times the square root of 3. So as long as they're like terms, as long as we have the exact same thing in both radicals, we can treat them like variables almost, right? So 6 plus 2 is 8, and we have 8 square roots of 3 now. Now we can do the same thing with the imaginary parts. So if we combine those, what should we end up with? Awesome. Positive I times the square root of 3. So we get 8 square root of 3 plus I square root of 3. Here's our real part. Here's our imaginary part. That's in the correct form, and that's our final answer there. Any questions on that one now? Anybody need more time to write any of that down? All right. So this is where this is really going to come in handy for us. Like I said, when we jump back into chapter 3, is actually solving some of these things and finding zeros of some of our polynomials. So let's take a look at this equation. So we got x squared plus 9 equals 0. Give you a minute just to get that copied down. Now, if it's a simple quadratic like that, remember we can just move the number value to the other side, and then we can take the square root of both sides. So in this case, I'm going to subtract 9. So that's going to leave me with my x squared on the left. And in this case, I get a negative 9 on the right-hand side. Now, to get x by itself, what are we going to have to do? Square root, right? Okay, so we want to take the square root of both sides. That's going to give me my x here. And what do we have to remember when we take the square root? Plus or minus, good. So this is going to be plus or minus the square root of negative 9 now. Okay. Now, at that point, we need to make sure we simplify. So what is the square root of negative 9 going to give us? Awesome. This tells us x is equal to plus or minus 3i, and that right there is going to be our final answer. So we have two solutions, positive 3i and negative 3i, right? And it would be I times the square root of 9, right? And then we just have to remember the square root of 9 is 3, and that's how we end up with plus or minus 3i here. Any questions on that one now? All right, let's look at this next one. So we got x squared plus 4x plus 5 equals 0. Again, we're solving the equation. Now, what I'm going to go ahead and tell you is normally you would say, well, let's see if we can factor it, right? But if I look at this one, my only factors of 5 are 5 and 1. And I know my signs are going to have to be the same to give me a positive 5. There's no way I'm ever going to get a positive 4x here. Okay, so this thing is definitely not going to factor. What could I do at that point then if I wanted to solve this if it doesn't factor? Awesome. Quadratic formula, right? Okay. Completing the square would also work, right? If you like completing the square, feel free to use that too. But quadratic formula will definitely always work. Okay, so let's go with that. So in this case, remember, quadratic formula is going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so what's our b value this time? 4. Good. So that's going to be negative 4 plus or minus. We have that same b value squared, so 4 squared minus 4 times, what's the a value? Good. And the c value? Awesome. All over 2 times a, which is just going to be 2 times 1. Now we need to simplify, right? So I'm going to try to wrap this one up because I know we're almost out of time. We got negative 4 plus or minus the square root of 4 squared is 16. And when I multiply this out, I'm going to get minus 20 all over 2 times 1, which is just 2. So when I combine my like terms inside the square root this time, I'm going to get negative 4 plus or minus the square root of negative 4 all over 2. And what should the square root of negative 4 be equal to? Awesome. So we're going to get negative 4 plus or minus 2i all over 2. And then if we want to put this into that a plus bi form, remember to split up the real and the imaginary part. So we have negative 4 over 2. That's going to be negative 2 plus or minus 2i divided by 2 is just going to be I. I just basically divided my real parts to get the negative 2, divided my imaginary part by the 2, and got the I here. So those would be my two solutions to that equation. Any questions on that one? All right. So before you leave, real quick, if I could, any issues today with anything that could be better before we pick up tomorrow with anything? Any suggestions that you've got? I'm always open to take those. So if you've got anything, I know it's tough, right? Especially when you can't be there and see me in class and that kind of thing, right? And obviously having to type answers instead of just being able to kind of spit them out, right? That makes a little bit of a difference. So German, you're having connection issues. Can you email me and kind of tell me what was going on, German, and then that way I can look into it and see, you know, if maybe there's anything we can do to help. You know, it may just be, you know, the amount of people on the network and stuff, but if you can kind of let me know what was going on, then I'll see if I can look and see if there's anything we might be able to do to help with that. Any other issues or anything people are having? And again, you know, you said, Naomi, you need to write faster, but if I am moving too fast, definitely slow me down. You can always just click the raise my hand, because that's a quick and easy way to say, hang on, slow down, you know, and I can hold up a little. Okay, so feel free to do that if I am moving too fast. All right. I don't have any other things. You know, I'll let you go because I know people have other places to be, and I do have another class coming up too. But if you do have any other suggestions or anything, please do let me know, and I will see you guys. And I hope you have a good afternoon.